Hey guys, this is Mechanics 2 Centre of Mass Part 1 short summary video. So the easiest type that we have at the beginning is this kind of thing where we have point masses. So this question tells us we've got these 3-point masses there, and we're going to combine them as if they were all one single mass acting at a certain point. So all we're doing is using the principle of moments, that the moments about the origin of all these three added together is the same as the moment about the origin of this single centre of mass point. So if I look along x bar is the distance of the x coordinate of the centre of mass. So 12 times that distance, x bar, that moment, is equal to the moment of this 4 kilogram force, which is 2 along times 4 kilograms. Moment of this 5 kilogram force, which is 3 along times 5. And the moment of this force, which this mass, is 3 along even, and times 3 kilograms. Now I've put minus because if we're doing moments about here, this one pulls it clockwise, this one pulls it clockwise, this one, hang on, is that clockwise? Yeah. This one is going to be pulling it anti-clockwise. Got my clockwise and anti-clockwise mixed up there. It's been a long day. So this one clockwise is equal to, is going to be, this one is negative, okay? Because it's going the other way. Anyway, right here, we work all this out and we get 14, divide, and we get x is 6/7. Okay, the y bar one, we're doing exactly the same sort of thing. The distance here, y bar, times 12 is equal to, we've got the positivity of this distance 4 times the mass of 4, minus, acting against it, acting the opposite direction, we've got this distance of, which force are we doing next? This distance here of 4, minus 4, times the mass of 3, and this distance here of minus 2 times the mass of 5. So this is positive and these two are negative. What you can do if you're having trouble visualizing this is imagine turn your page on its side. A lot of people prefer doing that, and then this will be taking it one way and these two will be taking it the other. That's why they're negative. So we get all this and we have minus 8, 12y, y is minus 2/3. So it actually makes sense because we've got y down here. It makes sense for the centre of mass to be more down here because you've only got one mass of 4 kilograms up there. You've got a 3 and a 5 beneath the line. Right, let's wake up. I need a little bit better explanation on this one. Keep pausing there. Pausing is bad. Indeed. Right, centre of mass. Now we're looking at right angled triangles. If we've got a right angled triangle, centre of mass of our right angled triangle is 1/3 of the way in from the right angle. There you go. So 1/3 of 3 is 1. 1/3 of 6 is 2. Boom, done. Easy. Now, other triangles, there's other things you can do. There's the centre of mass lies along the line which you get where you combine each vertex with the midpoint of the opposite side. So if I had a line across there, line down there, they'd all cross at the centre of mass. But that's a big faff. What it's easier to do really is either use this kind of idea or just treat them as point masses. So I thought here it would be good fun, in a mathematical kind of fun sense, to look at what if they were just 3-point masses. So from point A, x bar wise, we have got this distance of 6 times that mass plus this distance of 4 times that mass, so those are the two moments of those two, is all equal to the total mass of 3, 1, 2, 3, times x bar. So add those, divide. I haven't included that mass in this because I'm doing it from point A. It has no moment about the point I'm taking moments from. So do all that and I get 10/3, 10a over 3, which makes sense looking at the question. Here, y bar, so we're looking vertically. I've only actually got this mass acting vertically. along, so that's 6 times m is equal to the total mass of 3m times y bar. Divide those and you get y is 2a. And again, we see, look, a third of 6a, a third of 6a. Anyway, here, find centre of mass of compound shape, split it into sections. So there's no rule or formula for these compound shapes. So easiest to visualise them as area, really. So if you had the area, wanted to just find the area of that, you would do it as the area of one block plus the area of another. Now I've split it down here. You could have split it across here. I just split it down there, really. So if it's a uniform lamina, which it should have said there, but it does look in invisible ink, then its mass is proportional to its area. So we can say that the centre of mass of this block will act in the centre there, and that mass of that block effectively is its area of 10. Mass of this block, again is 10, and acts in the centre of it there, assuming this is a uniform lamina. So we've got the total total mass, which is actually area of all this, which is 20, is equal to the mass of this, which is 10, times its distance from the coordinate axes here of 1, plus, now here's a mistake a lot of people make, it's all from that point there. So when I've drawn the diagrams, I've purposefully kept my origin exactly where it should be, which is effectively there. So you include this whole distance, so that's 2.5 plus 2 is 4.5, okay? Because you're looking at the moment, effectively, of the centre of mass of that along this line, which is this distance times its area. Working all out, we get 2.75. Exactly the same for y bar. Total area is still 20, and that's area of 10 still, times 2.5, which is this distance here, and area of 10 times 1, which is this vertical distance here. Doing all of that, we get y is 1.75. Okay, that's me done. Goodbye.